Good morning everyone. Welcome back to the second day of Frontiers of Geometric Algorithms workshop. Today I have the pleasure of introducing our first speaker for the day, Professor Tamal Krishna Dey, who is a faculty at Purdue University. Professor Tamal did his master's right here at IISc and followed it up with a PhD at Purdue and a postdoc at UIUC. His research interests lie in combinatorial topology, geometry and data analysis, and today he is going to give us a talk titled Geometry Brings Persistence to Combinatorial to Dynamical Systems. So please take it.
Thank you. Before I start, I must thank the organizers. Let me spell the names: Pankaj, Arindam, Siddharth, and Rahul for inviting me to this wonderful workshop. For me, it's very special because I am returning to my alma mater almost 30 years after, so it has changed a lot, but still the main structure remains the same. So today I'll give a talk on something which I have been working recently on. My background is in computational geometry, but lately I work a spin-off from that computational geometry it's called computational topology and topological data analysis. So and this is, before I forget, this is a joint work with my student Andrew Haas and two of my collaborators, Michał Lipinski and Marian Mroziek from Poland. Okay, so what I'm trying to do here is to make a connection between two theories. One is persistence theory, which is a very recent phenomenon. Recent means almost 20 years, but in any scientific chronology, 20 years is nothing. And the other field is dynamical systems, which have been around for a long time. So between the two, I try to make a connection, and I believe there is a much stronger connection, and this connection makes us, the computer scientists, much more relevant because this lets us compute efficiently something in the dynamical systems. My only trouble is that these two theories, to explain in details, I need a little bit of background in algebraic topology. And there is no way I can try to introduce algebraic topology within even an hour. So I'll not try to do that. And everything I'll keep at very intuitive level. Whenever I say means or roughly means, behind that means there is a strong mathematical underpinning coming from algebraic topology, and the beauty happens there actually, the theory. But that theory enables the beautiful algorithms. So I'll tell you the magics of the algorithms, you can see, but probably I cannot tell you why the magic is working. You have to believe me. And if you still want to know, please talk to me offline. I'll be very glad to tell you why it is happening. Okay, so let me first start with the first subject, topological persistence. So topological persistence, actually before I even go there, one of the building blocks is called simplicial complexes. It's a very basic concept, and I have written, I came a little early, I have drawn there. So what is the definition of a simplicial complex? So let me tell you. So what is a simplex? Is the generalization of triangles. So a zero simplex is a point or a vertex, and one simplex is a segment or an edge. A two simplex is a triangle. The number denotes the dimension, and definitely three simplex is tetrahedra and beyond. Okay, so those are the simplices. A simplicial complex is a collection of simplices, okay, but it must satisfy certain condition. The condition is, I have written here. How is it defined? You first have a ground set V, we call it vertex set, and then K of V, the simplicial complex defined on this vertex set, is a collection of simplices. Say simplex sigma is nothing but a subset of this V. You have to somehow forget the geometry for the time being. So it's only a system actually. So it's a collection of subsets of V, which a simplex I am denoting as sigma. The condition is that every subsimplex of sigma is also in the collection. That's the only condition. That's what I have written here. And here is an example. For example, this is a simplicial complex. And what are the collection? The age AB, age AC. But since I have age AB, I have to include their subsimplices, which are vertex A, vertex B. And that's why I have AB, AC, A, B, C. Here is also a simplicial complex. It's like a triangle and an edge sticking out. But when I, this is a geometric drawing of the simplicial complex, but abstract simplicial complex is just combinatorial structure like all the vertices, all the edges and the triangles. You cannot just have the triangle and call it simplicial complex. You have to have all its faces. Okay, so that's simplicial complex. And this yes.
How do we define the edges? Like, we are only choosing the set of vertices, right?
So tuple is a edge. It's always it's only combinatorial. A triangle is triple.
So how do you generalize this? Is it just fully connected graphs, or like if I go to four
Graphs is a simplicial complex, but one-dimensional simplicial complex.
Okay.
So it's a generalization of graphs in a sense.
Okay.
But it's much more.
So, can you say that it will be power set of
Mm-hmm. So I could have written sigma belongs to 2 to the power v. Okay, so let me now proceed. Now this simplicial complex is the geometric connection between the two theories, because persistence works on something called homology. So it's a group structure, and this homology is defined on simplicial complexes. The special simplicial homology is called simplicial homology, and that's the building block of persistence theory. And the dynamical systems, there is nothing simplicial complex about it. Generally it comes from ODE or PDEs, the equations, but combinatorial dynamical systems, which is a very recent phenomenon. Now people can define a combinatorial dynamical systems on a simplicial complex. So that's the connection between the two. Okay, so now let me give you very briefly what is persistent homology in 5 minutes, okay? But again, I caution you, maybe I will not be that detailed and maybe I will not be understandable at all. So
Sorry, one question is that so this is very discrete definition, but
Mhm.
then
there is a geometric realization.
that is very continuous. So how?
So which one is continuous?
So the dynamical systems itself.
Yeah, you will come. That's the yes, that's one of the main thing. Okay, so here is a persistent homology. Persistent homology one can introduce to you in different ways, but I choose this particular example. Generally, persistent homology is defined. Okay, whenever you see persistence, topological persistence, it's a topological persistence of a function, not on a space. Function is a persistent homology of a function. That should be the first things to note. So here I and this function could be a function on a triangulation, or a function on say plane, or some d-dimensional space.
Or a group action. Or a group action.
Group action, you need a map, a function, one parameter map. Actually, it could be multiple, but I would not say group action. That will be a little bit too far away.
So not like the cohomology, where you're just dealing with homology.
Yeah, let's not go into cohomology because, but there is a dual, always something which is works in homology works also in cohomology, but you have to choose the coefficients properly, otherwise things, I will not go in there, okay. So, so let me take this example. Here is a point cloud data, and this point cloud data, what you can do, think about that a disk is growing centering each of the points. As you grow the disks, take the union of the disks, so the space is changing. It's a movie. So first I started with these points, discrete points, then you start growing the disks, the union of the disk is changing. From here I go here, sorry, from here to here to here to here to here. So movie is changing, the space is changing. and you look as the space is changing, how the connectivity is changing. So, for example, when I say connectivity, this is a very loaded term. Connectivity exactly is captured by homology groups. Okay. So, let me tell you what is a connectivity here. So, for example, zero-dimensional connectivity or H0 for zero-dimensional homology group is nothing but the number of connected components. So, here each of the points is a connected component by itself, but when you start growing the balls, they start joining. So connected components become less and less. And ultimately, if you see, they have become a single connected component now. So connected components, as I go through this movie, is continuously changing. Okay, so that means the homology A0, zero-dimensional homology is also changing. Okay, now let me go to the one-dimensional homology. What is one-dimensional homology? That also you know, in graph theory, you always talk about the cycles. Those cycles are nothing but they capture one-dimensional homology. Okay, so that is also changing. Look into this. There is no one cycle here at this point. Here there has formed a one cycle along this. So that's why this hole has been created now in the space and the complement space. And then again here another. So probably in this this is not a cycle yet because there is a gap here. But here now there are two cycles have been created. Okay, then as you grow the ball, this cycle really disappears. So that means H1, the one-dimensional homology, is also changing. New things are getting created, like one cycles, and some of the cycles are dying because they got filled up. Okay, persistent homology, what it does, it exactly tracks what is happening in this homology group. Like in H0, how the components are changing as I go through the movie, and how the H1, the one cycles are changing as I go through the movie. And whenever I say all these things, there is a very precise definition of algebraic topology which will concretize all these notions, which I am completely skipping. But the intuition is this. Okay, but the only problem is that with this growing space, it's very difficult to compute because then you have to compute the union of disk and think about it. This is only in 2 dimensions. In high dimensions, we will have the balls and computing their intersection and all this are not going to be easy. So one way out is that you map this space to a simplicial complex through the construct of nerve. This is nothing but a dual combinatorial structure which represents the connectivity of this space. And this is what I am getting. So initially this is a simplicial complex which is nothing but set of vertices. But here already the edges and triangles started appearing because whenever 2 balls intersect I put an edge, 3 balls intersect I put a triangle, it goes like that. And so you can see from here to here to here to here to here what is happening, more and more simplices are appearing. That exactly reflecting the fact that the space is growing. So this also means the simplicial complex is also growing. More and more simplices in these definitions are coming into the picture. And this is called a filtration. A filtration is a sequence of simplicial complexes such that if you go from I to I plus 1, the complex grows. So there is a map from I to I plus 1 by inclusions. And once you have this, now you can study what is happening in the persistence in the simplicial filtration. Okay, which will ultimately mimic the filtration of the original growing space of the union of disks. So in this case, for example, let's track. So this is the A0 and this is something called the barcode. Barcode is the ultimate output of the persistence algorithm of persistent homology. It's like something like creating a signature of this point cloud data. Okay, so what is the signature? And that's why it's called barcode. It's like lines. So for example, it will track what are all these vertices. They are creating in one component each. So that's why I have all are created at this point. And as I go with the time, like this sequence of the movie, what is happening? So for example, here already some of the components have merged. So that means some of the components has already died. Merging means it has been killed. They are not individual components anymore. So that's why this one has, these are dying here. Then some more are continuing and ultimately dies here because there are only 3 components. So that's why only 3 are surviving beyond this point. Ultimately 2 of them are also dying here. There is only a single component which now it continues all the way. So that's the diagram you get. So for one dimensional, which is H1, look into it. For example, there is a cycle which is born here. So you get a point because it has born, and this cycle goes from here, ultimately dies here. It got filled up. So that means this cycle got born here and ultimately died here. So I get a bar for this cycle here. The other cycle which gets created here, probably here, and it didn't die, at least in this, not in this movie. If I would have continued, ultimately it will die, and I just put it here. So you get 2 bars here for H1, which are very prominent bars. There are other bars also I am not showing, they are the noise, the small bars. So what is happening from this movie, what you get, these bar structures, and the long bars will tell you what are the prominent features which was ultimately coming from this point cloud data. Now we can relate from the data analysis all the things we want to do. We want to extract some features and analyze with it. And this gives a mechanism of extracting features out of the data. But no feature extraction is very good if it is not robust against noise. Because if I perturb the data a little bit and if my signature completely changes, that's nothing good. Okay, so it should be stable under noise, and that stability also is proved, and it happens with persistent homology. So for example, let me again illustrate this. So here is one can use persistent homology for clustering. Here are 2 clusters of point cloud data. If you do this movie what I just did, you will get all these bars. There are all little bars, but there will be 2 bars which are very long, and they signify there are 2 prominent components. Okay, but if you do the H1, there is no prominent 1 cycles here. So you will get in H1 all small bars. There are no significant bar in H1. However, if you take this data, which is also 2 components, but suddenly now this data is different from the previous data because now there are 2 cycles are also there. What will happen if you do the H0, you will get very similar as the previous one, 2 prominent bars, but what will happen in H1, now there will appear 2 prominent bars, which was not there previously. So this will distinguish that this data set or this clustering is different from the previous data. Okay, so that's the power of persistent homology. And also, as I said, it should be stable. So instead of this data set, if I perturb the point set a little bit, so this point set is a little bit perturbed version of the previous one, you can see these 2 bars, and the 2 bars remains almost same. It did not affect the length of the bars. Again, whenever I say these things or intuitively, everything can be proved very precisely with mathematical theorem, that what do we mean by perturbation and everything, what do we mean by stability. Yes?
Is noise dependent on the separation that you have?
Well, I just chose to perturb the point set here ultimately. I did not do any particular coming from a particular distribution or something. Yeah, of course, what the stability says, that stability is within the, like, it's stable up to the noise. If you perturb too much, nothing can be said. It's always bounded from above by the noise.
How are these barcodes related to these Betty numbers?
Well, Betty numbers are generally dimensions of the homology, right? So dimensions of the homology, meaning how many generators are there to generate that group. Okay, so Betty numbers is exactly the dimension of the homology group, and at any point on the barcode, if you count the number of bars, that's exactly your Betty numbers.
Capture the structure, but does it also capture the size? For example, if there are 2 clusters, but one is really large cycle, other one is small cycle, does it captured by age?
Yes, it will ultimately. So small cycle will die much earlier, and largest cycle will die much later. So the bar corresponding to the largest, that's what actually happened in the first example. So the length of the bars will tell you. But in a sense, you can see this entire mechanism is scale insensitive because it's capturing the features at every scale. But if there is a prominent feature which stands out from the noise, then it will give you also the bar which stands out from the rest. So that's the whole. Okay. So now, how do you compute these bars? So these are all these theories of concepts. How do you compute? There is a wonderful algorithm which is a variation of the Gaussian elimination actually, which can be done on the matrix algorithm. How does the matrix comes into picture? Again, here is an example of a simplicial complex. It's a tetrahedron. Okay, and as I said, persistence is dependent on a function. So I have to define a function value on each simplex. So I am denoting, for example, this age is 1, then this age is 2, this is 3, this is 5, this is 6. So take them also as the value of the function on the simplices. Also the the triangles also have value 7, 8, 9, 10. Okay, for simplicity. So what is happening, this simplicial complex is filtered by first of course I have to bring in the vertices which I am not showing here. First suppose all the vertices have come in, then this first h comes 1, then 1 and 2 comes, then 1, 2, 3 comes here, then 1, 2, 4 comes here, 5 comes here, 6 comes here. So far everything is graph because it's only vertices and edges. Here starts coming the triangles, 7 come here, 8 come here, and think always, since I have to remain as a simplicial complex, any simplex can come only if all of its faces have already come, otherwise it cannot be a simplicial complex by this definition here. Okay, so this, in this particular example, this is a simplicial filtration. It's a sequence of simplicials of the tetrahedron. How do I compute for this simplicial filtration? How do I compute the bars? With respect to the function value, bars, the endpoints of the bars are nothing but the values of the function, which I have taken here. Okay, so what you represent this filtration with a filtered boundary matrix. Okay, I am going to define what is the filtered boundary matrix. A matrix you form if there are n simplices, suppose there are n simplices ultimately coming. So in this case, what will be the total number of simplices? 6 edges, 4 triangles and 4 vertices. So whatever it is, 6 plus 4, 10 plus 4, 14. There will be 14 simplices. I did not take the tetrahedron actually. So it's a simplicial complex. I took only up to the triangles. Yeah, you could have taken the triangle. So 14. So this matrix ultimately will be 14 by 14 matrix. But I am not showing the 14 by 14 matrix. I am showing only the part where the triangles have come in. Okay. The columns and rows of this matrix are the simplices. Okay. And the indices are exactly the function values. Okay. You sort the columns and rows with respect to the function value. In the sequence they appear in the filtration. So that's why here the triangle 7 came, 8 came, 9 came, 10. That's the order. And similarly the rows, all the rows 1, 2, 3, 4, 5, 6. These are the edges. I tell you why this. I drew this partial matrix. This is called the boundary matrix. Why it is called boundary matrix? For every column, for example, triangle 7, what are the entries in the column? It's exactly its boundary edges. So for example, triangle 7, look into triangle 7, its boundary edges are 1, 3, 6. And exactly it has 1 in 1, 3 has 1, 6 has 1. Okay, so that's the way you build this particular partial matrix for the 4 triangles. Okay, I am assuming everything is operating under Z2, meaning only binary operations. Okay, for simplicity, this is enough for explaining the ideas. So
Generalization of the vertex incidence.
Exactly, is incidence matrix, but the theory is available for any field actually. I am just taking this particular Z2. Okay. So let's see. So suppose I have gotten this filtered boundary matrix from this filtration. So filtered boundary matrix in a sense represents the function because you have taken the order. Order is very important. Okay, the simplices. Now this matrix reduction, it works as follows. What it does, it looks into the lowest entry where it is 1. That's called the pivot. So in this case, the triangle 7 and triangle 8 has a conflict in the pivot row. Both are 1. Whenever there is a conflict, you add from left to right the column addition. So, and again, this is a Z2 addition. 1 plus 1 is 0. Okay, so if I add this column to this one, what do I get? I get exactly this column. You can verify. This has been zeroed out because 1 plus 1 is 0. Okay, so now the algorithm proceeds by looking from left to right the columns. Whenever there is a conflict in the pivot row, it will add that column to the right. Okay, so for example, as I added 7 to 8, I got this one. But now 8 and 9 has a conflict. Again, you add 8 to 9, you get this. 9 and 10 has a conflict, you get to this. Ultimately, after this process, what will happen? Every column either has a unique pivot row, which is not claimed by anybody else, or the entire column has been zeroed out. That's what has happened. 10 has been completely zeroed out. And once you have that, this is called the pairing. What is happening that the triangle 7 has been paired with the edge 6. And whenever this pairing happens, this means the cycle created by edge 6 is killed by the triangle 7. Remember, there was a birth and death, I said, and now the algorithm detects this way. It's a magic. Why it is happening? Again, all these things can be explained through the algebraic topology, through homology. Okay, so there is a pairing 7 and 6, there is a pairing 8 and 1, and you have the bar. 6 and 7 there is a bar, 6 to 7. Then from 5 to 8 there is a bar. Then 4 to 9 there is a bar. And that's it. And 10 does not have it has a bar wherever it happens first, but then it continues all the way. Infinite bar. So this is an algorithm called the matrix reduction. This left to right column. It's a very simple algorithm, but it gives you all the barcodes. Okay, in every dimensions actually. Remember, this one you will be doing with this larger matrix, which has all n by n matrix, and you just go on doing it. Okay, and why I say magic? For example, here when I pair 7 with 6, 6 has to be a cycle. 6 has to be an edge which must create a cycle. You are not doing anything in the algorithm, but automatically it happens. It's guaranteed. Whenever there is a pairing, there is a cycle structure created at that moment.
So 6 created more than one cycle? No?
Yes, you can say. So whenever 6 created, yes, whenever 6 creates, it can create more than one cycles, but we always talk about the number of independent cycles. And the number of independent cycles means basically in the homology group whether a new basis is created. Remember, whenever a basis element comes, many new elements are generated by the addition of that basis element with everybody else. But independently only one. The dimension increased by 1.
But isn't it true?
It is.
Two independent?
No, well, they are independent, but it's not that one can be, if you take only one cycle, it can be written as a sum of other 3. Okay, so that way it is independent.
But they're not all killed by 7.
No, okay. So when the killing happens, then it will kill a unique cycle the algorithm determines. And that's why this unique low one. So whenever a cycle is created, yes, you can say many cycles are created, but only one independent cycle is created. In the sense the dimension has increased by 1. When killing happens, also dimension goes by 1, goes down by 1. Yes.
This pairing is not unique.
It is unique.
You have to order the 7, 8, 9, 10, or you can actually.
No,
take one.
unique up to the order. Once you have fixed the order, then it is unique. And as I said, persistence is only for a function. So and function is given by that ordering. Once you change the ordering, then you have taken a new function. It's a new persistence. Okay. So now I come to the vector field part. So this is the persistence. Vector field, as somebody was telling me, okay, yes, vector field is continuous. Here I am showing you a continuous vector field, only some of the sketches of the integral lines given by the vector field. Okay, but this is not good for us, for computer scientists. I cannot compute with this. Okay, suppose it is given by a ODE or some equations or something, it's not good for me. What we can do, we will go to continuous to discretization. There is a discretization process. First, for the discretization, I have to discretize the domain on which the vector field is defined. So you take a triangulation, for example here. There is a triangulation, and the vector field I am showing still are continuous lines, the integral lines. Okay, and the vector field has all these critical structures, repeller, the repeller, attractor, and all those things. Okay, I'll come to these points later. And we are going to now also discretize the vector field, continuous vector field, using some combinatorial structure. I'll tell you in a moment what is that. So I'm going to define what is a combinatorial vector field. The combinatorial vector field is defined as a partition of a simplicial complex. So you take the domain K as a simplicial complex, and then you partition the simplicial complex into it's a collection of simplices. That's the vector field. But this partition has to have some certain condition. I say a multivector, here is the definition. Multivector V is a subset of simplices. Only thing is that if sigma and tau belongs to the vector V, then all the faces in between sigma and tau here by the face relation has to be also in the same vector. So it's convex with respect to the face relation. Or if you think about the face poset of the simplicial complex, then it is convex with respect to the face poset. So what does it mean? Let me just tell you. For example, let's take this. This is going to be a vector field. A particular vector. Vector is a triangle, two edges, and this vertex. So I take the vertex, two edges, and the triangle as a vector. Okay. So you have to be a little bit open to accept it. This is a vector for my definition. It's not like a vector like that. So it's a collection of simplices as a vector. Okay, and for visualization purpose, I am showing the arrow. Arrow is from the vertex to the top dimensional simplex. The edge to the top dimensional simplex. The convexity condition here means if you have included vertex and triangles, you must include the two edges also in your set. That's the condition. That's called a vector. Okay, and what is a vector field? A vector field is the partition of the simplicial partition, not decomposition. It's a partition of the complex into vectors. Okay, so here I am just showing different combinatorial vector field on this simplicial complex. Okay, so this is the definition. Now let me go to the next one. So what is the connection between this commutatorial vector field and the continuous vector field? I am going to give an intuitive idea here with this picture. Yes.
Sorry, in the previous slide, can we just include a triangle in a multivector?
Yes.
Not the edges?
Yes.
So it's not a simplex in itself.
Triangle is a simplex.
Sorry, as in like a simplicial complex. Sorry.
Yes. A vector need not be a simplicial complex. It's a collection of simplices satisfying this condition. Okay. Yes. So a triangle by itself is a vector. Not only is a vector, it's a critical vector. It turns out to be actually I am coming to that. Maybe the next example. Okay. So let's take this simplicial complex. Very simple. A triangle. Triangle, three edges, three vertices. Nothing. Very simple. I am going to define a multivector field on this triangle. Various types of multivector field you can define. Here is one example. I take the multivector, it's a partition, remember? So one vector is A and AB. So this is one vector. B and BC is another vector. And then AC, and the triangle is another vector. So there are four vectors which has partitioned this simplicial complex. And these four vectors actually signify a flow like this. So what is happening? Things are flowing here, and then ultimately C is the attractor. C is by itself, is the attractor. So flows are coming like this, flows are coming and attracted here. All the flows are coming here. So that's the significance of this vector field. Let's take another multivector field on the same simplicial complex. Here I partition, this is one vector, B and BC another vector, C and A another vector. So this is, you can see this 3 vector is making a cycle now. Okay, and the triangle is by itself. Now there are again 4 vectors, and this is a multi-vector field. This multi-vector field is showing that from the center of, or you can think of as from the center of the triangle, the flows are going around, then coming to the boundary, and then it's stuck in this orbit.
So in the first triangle, isn't that the vector from AC, B is the attractor and Y the flow is going to?
What B to C, yes.
No, but this one, yes.
So this comes from the edge, as if things are coming into the triangle, and then they are flowing to the here. You think that way, okay? And so this is very interesting. It's like a cycle, it's like an orbit, and there is a repeller. Okay, this one is also another multi-vector field with 4 vectors. What I did, one vector has this vertex, 2 edges, and the triangle. The other 3 are B, C, the 2 vertices, and the edge by itself. So in this case, think about it, what is happening, this integral lines, as if all these things are flowing, one part is going to this attractor, another part is going to this attractor. This is like a saddle. So all these vectors fields, they come here and they bifurcate. So saddle is the structure where things come in and then it goes down. So this edge is now acting as a saddle, and these 2 vertices are acting as an attractor. Here is another, so on the same simplicial complex I have another vector field, but this vector field has only 3 vectors. One is very large vector with everything else, B and C. Without these 2 vertices, everything else is another vector. So that will signify that actually this will be critical. This is like all the flows are coming to B, coming to C, and also something is coming here. So this one is now acting as a saddle. So you can see by a simple triangle you can have multiple ways of defining the actually simulating continuous concept into combinatorial concept. Yes.
So I'm thinking kind of extension of the Forman style discrete vector.
Yeah, this is yes.
Right. So is there an equivalent way to? I mean, can a multi-vector be considered kind of essentially
as
as Forman's?
Yes, of course. So Forman defined this. Actually, this entire theory started with the Forman's vector field, and this multi-vector field is more powerful because it generalizes the Forman vector field. So Forman vector field, it always allows you to have I have only 5 minutes. Allows you 2 simplices or a single simplex, but multi-vector allows you multiple simplices. Okay. So for example, the entire simplicial complex I can define as one vector.
Right. So my question is, can I, given a multi-vector field, can you rewrite it as the
Not always.
For a different simplicial complex?
Not always. So multi-vector field is distinctly more powerful than Forman vector.
Okay.
You can do certain things with multi-vector field which you cannot do with Forman vector. Okay, so what do I do? So now I have to define in the combinatorial terms the integral paths. Okay, so integral paths needs a definition of a flow. Okay, so how do I define the flow? It's defined by a multi-valued map. So if V is the flow, what it does, it takes a simplex and it maps to a couple of other simplices. That's why it's called multi-valued map. What are the other simplices? It takes the simplex and it can map to any simplex within its vector, or it can go to its boundary. So that's the second part. So this is within the vector or it goes to its boundary. Okay, so let's take so in the let me see, do I have, okay, so I'm coming to that. Okay, so that's called the flow. And what is a path? A path is a sequence of applications of these atomic flows. Okay, so basically a path, I start from a simplex where I can go. That will give you a path through this multi-valued map. Okay, so that will simulate the integral paths in the vector field. Okay, and then there is this concept of Morse set. So Morse set is nothing but a collection of again simplices such that if you take a path within the set whose endpoints are within the set, then entire path has to be within the set. So then it's called a Morse set. So a Morse set means if you are remaining within the set at the endpoint, the entire path has to be. Otherwise, if you exit, you cannot come back. That's what it means. Okay, so here is again some example. Here I have taken a dynamical system, sorry, not dynamical, a smooth function on a sphere. Okay, so the Morse set now is defined by these 4 critical points. This is like a repeller. This is like a repeller. This is like a saddle. This is like an attractor. Okay, so it is coming. So I took it as a gradient function. There is no orbit. So once you have the gradient field, there cannot be any cycles. There is no curl. It's only the div. Okay, but in general, dynamical systems is much more than the gradient field because it can allow cycles, and that's why it's more complicated. Okay, but in classical Morse theory is defined on the classical Morse function, which will give you the gradient field. So here is the gradient field. A connection matrix is nothing but it will summarize the vector field by telling you from which critical points where you can go to which other critical points. For example, in this here, I can go from B to C. So I have B to C, there is a 1 here. I can go from A to C, I have a 1 here. But whenever you say you go, you always say that you can go by decreasing in dimension by 1. So
for
yeah.
sphere, for sphere, how do you determine the saddle point? Is it any point on the equator?
No, in this particular case, I just took this. Okay, so in this case, this is the saddle point. I just took an.
How do you get that saddle point?
No, this is by example. I'm not computing it. Okay, just to show. This is suppose this is the critical point. But ultimately, you summarize this entire vector field by this matrix, which is called the connection matrix. It summarizes the flow from where you can go where. Okay, that's called the connection matrix. Here is another one example. Now, here is the example which I am defining on a disk. It's a continuous field now again, but this is not a Morse field or Morse function defined by Morse function, because now you can see I allow an orbit around the cycle, which was not here. So now I have a critical repeller, saddle, and then I have the orbit. Orbit is an attracting orbit. Once you are in the orbit, you are stuck. You cannot go anywhere. Orbit could be also repeller. All different types of structures are there in the dynamical system. But you can discretize it, as I said, using the multivector field. So this will mimic some of this field. Look into it. Like I have drawn the arrows to tell you. And once I have this discretization, I can define the connection matrix from this discretization. And so this connection matrix ultimately, if I have discretized well enough, will capture the connection matrix of the continuous vector field. And that's the goal. How to compute the connection matrix from this discretization. Because then I have a summarization of the entire vector field. How much time do I have? I have 0 minutes. So I cannot even tell you the main algorithm I wanted to do. So let me not, just to tell you one thing from the computer science, you can compute this Morse sets or Morse decomposition using our favorite algorithm on directed graph, strongly connected components. The strongly connected components in the directed graph corresponds to Morse decomposition. It's a finest Morse decomposition. So I can compute it, and then I can set up this boundary matrix again, and on this boundary matrix now you can do something like a persistence. Let me skip a persistence algorithm, but this persistence algorithm not exactly the persistence algorithm, because definitely it's not exactly the persistence, but there is a twist. The twist is only to recognize whenever you add from left to right the columns, you have to restrict this addition. Certain columns can be added, certain columns cannot be added. Once you do that, you have gotten the connection matrix, and then from the connection, I cannot just go over the algorithm. I thought I will have enough time, but I don't have the time. But you get them, so magically you obtain this connection matrix through this matrix operation. This is the newest algorithm. This has not even been published yet. And this is the very simple algorithm. We never thought that the two theories are so close together. The connection matrix theory is, it has been worked out. In my opinion, it was very complicated when I first read it. But now I see it very clearly how once you discretize it properly and interpret everything properly, things becomes very clear that they are very close together actually. Now we can compute this connection matrix much more efficiently using our favorite softwares in persistence. So let me just tell you. So previously there was another algorithm by us 2 years back. That the new algorithm actually has really simplified that algorithm. Previously, which like here 55,000 simplices, it took 20 hours previously. Now it takes only 1 minute 51 seconds because of this simplification. Okay, so that's the gain. And of course, the second part is you can define, persistence defines the concept of signatures on a scalar field, a function defined on a domain. Now we can define a persistence on a vector field, which was not there. So we are defining a persistence on a vector field on a domain, and now you can compute again signatures of the vector field. You can compare the vector fields using those signatures. Those have not been done yet, but that's the future agenda. I have put my students to work on it, and hopefully at some point we can use this technique for the data analysis with the vector fields. Thank you.
Do we have questions?
Any
Your time for
background references? Any good background references?
So what you can do, you can look into. I kept on giving this paper. If you go to this paper, then there are you can see the main references there.
So, next up we have Professor Sharath Raghavendra, who is a faculty at North Carolina State University. Sharath did his PhD at Duke University and then followed it up with a postdoc at Stanford. He works on problems related to matching and optimal transport and is a co-founder of Decaltra LLC, a startup focused on decision algorithms and transportation. Today he is going to give us a talk titled Fast Scaling Algorithms on the Semi-Discrete Optimal Transport Problem. So join me in welcoming Professor Sharath.
Thank you. Can you guys hear me? In the back? Okay, good. Yeah, so my talk today is about the semi-discrete optimal transport problem. It's a very nice geometric problem, and what I'll do is I'll try to sort of present new algorithms for these problems that are motivated by graph algorithms on cost scaling algorithms on graphs. So you'll see hopefully a connection between an interesting geometric problem and some graph theory techniques. So I'll begin by introducing the semi-discrete optimal transport problem, and then what I'll do is I'll basically present a cost scaling algorithm for solving this problem, okay, this geometric problem. I'll conclude with a couple of open questions. So what is the optimal transport? You're given two distributions, let's say this blue distribution and the yellow distribution. And let's say if you want to transport delta mass from x to y, the cost associated with that is delta times the distance between x and y. Okay? Suppose that is the case, then the optimal transport problem asks you to transport all the mass in this blue distribution to the yellow distribution in the cheapest possible way, the minimum cost way, right? And the cost associated with that is called the optimal transport cost. If two distributions look similar, the OT cost or the optimal transport cost will be small, and if they look very different, then the OT cost will be high. So it becomes a very interesting dissimilarity measure between probability distribution, and it has found a lot of applications in machine learning where you're trying to train models, and one way to do that is to understand how far away is your model from real data and fix the model accordingly, right? So optimal transport, due to various reasons, for instance, it's differentiable costs, so it is used in the as a loss function by training neural networks. In its most general form, the problem is defined on two continuous distributions, right? So you can think of this distribution, for instance, as the real world, data distribution of real world data, and this as the model, the neural network, right? And one may want to compute the optimal transport between these two. Unfortunately, though, we don't know how to deal with continuous distributions when it comes to algorithms. So what we typically end up doing is we take samples from these distributions. So we take samples from both of these distributions, and then take the empirical distribution here and compute the OT cost between the two discrete distributions. Okay?
So in the discrete version is like min cost flow.
That's right. So a standard algorithm for solving this problem would be simply model this as a bipartite graph and solve the transportation problem, min cost transportation problem on it. Right? Now this is an interesting intermediate problem, which is you're given a set of discrete samples, let's say real world data, and a neural network which is a continuous distribution. Can we compute the cheapest way to transport mass from this discrete distribution to this continuous distribution? Right? So that's the problem, the semi-discrete optimal transport problem. So let me define it a little bit more formally. A semi-discrete optimal transport plan is simply, tau can be thought of as a distribution over A times B, where A is the support of the continuous distribution, this entire space here, and B is the support of the discrete distribution, right? And what is the property we want? We want tau to be a distribution whose marginals are equal to mu and nu. What does that mean? It means that if I take a point here in this space and take tau AB for all the B, the support of the discrete distribution, and add them up, that should be equal to mu A. And similarly, if I take the support of the discrete distribution, any point in the support, and integrate it over the entire space A, tau AB on the entire space A, that should be equal to mu B. They're essentially saying that the mass from this discrete distribution is being transported entirely to the continuous distribution. Any questions? And the cost of the transport plan is simply given as follows. So if you have between A and B, suppose the transportation is tau AB, then the cost associated with that, there's always a parameter P associated with this. So let's, for this talk, assume P is 2. So what you do is you simply multiply tau AB with the squared Euclidean distance between the two endpoints, A and B. That will be the cost of between the edge A and B. Now to get the overall cost, you simply have to add across all points of the discrete distribution and integrate across the entire space the support of the continuous distribution. So that is the overall cost of the transport plan. And of course, the optimal semi-discrete transport plan is the plan with the minimum P versus time cost, and that's what we are interested in finding. For this talk, I focus on computing epsilon close semi-discrete transport plan, which is basically any transport plan whose cost is within an additive error epsilon from the optimum. Yeah.
So why are you looking at this problem? I mean, it's not just a discrete problem, which is nice.
This is more preferable. Like if you just sample from a continuous distribution, you're prone to errors, sampling errors, right? So this would give you more stable and better results.
So tau is a distance function, or what is tau?
Tau is think of it as flow in the context of graphs. So if it was a purely discrete problem, then for every edge you'll assign a mass, right? The mass that's flowing on the edge. So this is similar to that.
So this a minus b to the power p, that cannot be incorporated in tau itself. It has to be separate.
Yeah, this is the flow. This is the cost of the edge, right? Yeah.
Why not the other one? The reverse direction, is this somehow easier than transporting a continuous to discrete?
No, both are it's symmetric. It's one and the same. Yeah. So it doesn't matter which distribution you start with. It's the cost will. I mean, the optimal solution will be the same.
It's a metric.
It is. Yes. Okay. So why is this an interesting geometric problem? Perhaps one reason is that it's very closely related to the weighted Voronoi diagram, and I want to make that link. Establish that link. So for that, let me explain what weighted nearest neighbor or weighted Voronoi diagrams are. So let's define the weighted distance, right? So imagine you have the support of your discrete distribution. Now imagine a set of weights assigned to this. So YB is the weight assigned to the point B, one of the points in the discrete distribution, right? So the weighted distance of any point A to point B is simply the distance between A and B minus YB, okay? Minus the weight of that point B. And the weighted nearest neighbor for any point A is simply the point of, among all points of B, the one with the smallest weighted distance, right? So if I give you any point in this space, the smallest point with the smallest weighted distance will be this point. All of these other points will be further away from the point A, right? So yeah, the Legouer cell or the weighted Voronoi cell is simply the set of all points whose weighted nearest neighbor is this point B. So Legouer cell of B is simply the set of all points in the support of A whose weighted nearest neighbor is B. Okay, and Legouer diagram or the weighted Voronoi diagram is simply remember each of these red points have a weight associated with it. So you can partition the entire space into cells, one for each point in B, such that if you look at the points inside of these cells, the weighted nearest neighbor is this particular point, right? So, okay. Alright, so what is the link with the semi-discrete optimal transform?
While you're drawing it as Voronoi, it's not clear that it will be convex. So the regions will be.
So if you assume P equal to 2 and the Euclidean distance, it turns out to have nice structure. It is these cells, no matter what weights you assign, these cells turn out to be convex. But for L1 and weighted and other distances, other P's, this may not be the case. Okay, so what's interesting is that solving semi-discrete OT reduces to computing a set of dual weights for the points in the support of the discrete distribution, such that the following property holds. So if you take any point B in the discrete distribution, then the mass at B should be equal to the mass of the continuous distribution in the Legler cell of B. If these two match up for every point, then that would correspond to the optimal transport, the semi-discrete optimal transport plan. And the plan itself is simply this: take the mass at B and transport it to the mass inside the Legler cell. Okay, so it's a very nice structure to this problem, to the optimal solution.
So what's the dual weight? Is the dual weight?
Sorry, wait. Basically, what we want to do is assign weights to these points. As we assign different weights, the Voronoi cells will look different. But we want to make a weight assignment in such a way that this property holds. The property that I said, that if you take the mass at B, that mass inside of the continuous distribution inside of the Legler cell of B is equal to the mass of the discrete distribution at B. Right? So the weights assigned that you assign to these points are often referred to as the dual weights.
So are you like translating the continuous? Wouldn't they have different supports?
Yeah, even if the supports are different, you can assign weights in such a way that the Voronoi cells will get then translated.
So there's always a solution.
This is always the solution. Okay, there's no known exact algorithm for these problems, for this problem in its most general form. And most of the existing solution compute epsilon close transport plans. Generally speaking, this is how they work. They start with some weight vector. For each point in the discrete distribution, you assign some weight. Compute the weighted Voronoi diagram. Now check if the mass at B and its Legler cell, which one's larger, and appropriately fix the weight. Do some sort of gradient descent on the weight vector to get closer and closer to the optimum. And if you run sufficiently many iterations, then it turns out you can get epsilon close to the optimal semi-discrete optimal transport. But the number of iterations you need typically is polynomial in 1 over epsilon. The other method is sampling. Basically, you take a sufficiently large sample from the continuous distribution, and then treat it as a discrete distribution and compute the discrete optimal transport between them. And when you do that, even there, you get an epsilon closed transport plan, but the sample size oftentimes is polynomial in 1 over epsilon. So the running time turns out to be typically in this case n to the O of B poly 1 over epsilon. It's known that it is sharply hard to obtain algorithms that are polynomial in both D and log 1 over epsilon. Okay, so the question that we asked is, can we design algorithms that are that have an exponential dependence in D, but whose running time is like polynomial in log 1 over epsilon, right, and not a polynomial in 1 over epsilon like the previous algorithms.
D is the ambient space of the support of.
That's right. D is the space in which the distribution, the dimension of the distribution. So here's what we have. There is one of the results we have. We give an algorithm that runs in time n to the O of B log diameter over epsilon. So this is the diameter of the union of support, and it also depends on a parameter phi. Essentially, phi is the time taken to compute. So if you give me a triangle, what is the mass inside the triangle? I need to determine that to run my algorithm, and we are assuming that phi is the time taken to get that value. Okay. And our main idea is to adapt the cost scaling paradigm that's very well known and well studied in the graph context for this problem. Okay, what I'll do is I'll describe the algorithm. It's very simple, very nice, and then after that I try to give an overview of the proof, like explain why it works, and then I'll explain how I can improve this further. Okay. So our algorithm will run the log delta over epsilon scales, the log diameter over epsilon scales, and just initially the scale is set to the diameter, and basically what happens is you run an algorithm inside each scale, and at the end of the scale you set delta to delta over 2. Correct? And you keep repeating this until the delta value falls below epsilon. So the number of scales turns out to be roughly log diameter over epsilon. What do you do inside each scale? You basically compute a set of weights for B and a delta closed transport line. Okay, so that's what our goal is. So at the end of, within each scale, you take the weights that you computed in the previous scale and update them to get a delta closed transport plan for this scale. Okay, so what that means is at the very end, when you fall below epsilon, you would have an epsilon closed transport plan.
Delta close to the optimum.
Yeah, delta close basically means that the cost of your transport plan is delta away, additive error delta away from the optimum. Okay, and
Additive or additive error?
additive error, yes.
Because I mean there's a upper bound, right? Delta times 1 is the maximum. I mean capital delta times 1 would be the maximum.
That's right. So we start our scale values initially starts with the diameter, and we keep reducing it until we reach epsilon, right? So, okay. So visually, this is what's happening. Our weights initially are not very stable, and you'll see that as the scales progress, the Voronoi cells will keep moving around, but afterwards it becomes very stable, and the boundaries will move very little bit. And let me describe what the algorithm does in each scale. Here's what it does. Now remember, at the beginning of scale delta, we have some weights that were computed from the previous scale, which is scale 2 delta, right? So we start with that, and this black edges highlight the weighted Voronoi diagram you have with respect to scale 2 delta. Now here's what you do next. You compute 4n plus 1 shifts of the Voronoi cell of B for some point B. And what is the shift? It's just the following. I'll not change the weight of any of the other points, but I'll increase the weight of B by delta. That gives me one shift of my Voronoi cell, which means I'll get an expansion of this Voronoi cell by some value, right? So that would be the one shift. And then to get the 2 shift, I'll increase this by 2 delta, and 3 delta, and 4 delta, and so on. So I'll get 4n plus 1 such shifts. What I do next is I take the arrangement of all these Voronoi cells, and once I take the arrangement, for each cell of this arrangement, I'm going to just place a single point and set its mass to be the mass inside the cell. Okay, so basically I discretize my continuous distribution now. What else do? I create edges between the points of B to these cells, or the representative of these cells, and I'm going to give them weights. If this cell is in between the ith and I plus first shift of the weighted Voronoi cell, then I give the weight of I plus 1 to the edge from the point of B. For instance, this point here is between the first and the second shift of the weighted Voronoi cell of B prime. So I'll give it a weight of 2. Okay. And if a cell is outside of all of the 4n plus 1 shift, then I'll just give it a weight of 4n plus 2. Okay. So if anything in this region outside of the 4n plus 1, the edge between B prime and that particular cell will be 4n plus 2. Okay, so this is how I discretize I create my instance of discrete OT assigned n to the O of t. Okay. So that's my first step of the algorithm. This is what I do. Next step, I'm going to simply solve the discrete OT instance.
Why is the size of the instance n to the order?
Oh, this is because of the complexity of the arrangement. In D dimensions, if you take Voronoi, these weighted Voronoi cells and their arrangement, the number of cells you get is n to the O of t. Right. So you create your a discrete instance and basically you solve it using any primal dual OT solver, discrete OT solver, and you get a set of dual weights that, since it's a primal dual discrete OT solver, it will give you the optimal transport plan as well as a set of dual weights associated with that optimal transport plan. And then you simply update your dual weights for this scale to be the old dual weight plus delta times the weight that was returned by the OT solver. And that's it. And then you update the scale and you continue. This is the algorithm. Okay. So why does this work? Essentially, you can view this as the following. So for the proof of correctness, just imagine one way to obtain delta closed transport plan is the following. You can discretize your continuous space into a set of regions, exponentially many regions, right? And one way, and then so basically replace each region with a single point like we did before, and then solve a discrete OT problem, right? One way to do that is we can basically assign weights to the points of B with the following restriction that the weights have to be integer multiple of delta and between 0 and the diameter, right? So we try out all possible weight vectors with this property that the weights are delta, integer multiples of delta and between 0 and the diameter. And for each one of these weight vectors, you'll get a weighted Voronoi diagram. You can take the arrangement of all these weighted Voronoi diagrams, and that would be exponential in, basically the number of cells in that will be exponential in n1 over delta. And then you can do the same thing we did before, replace each region with a single point and solve the discrete optimal. And essentially solving the discrete optimal transport problem boils down to solving these or maintaining a feasible transport plan that satisfies these properties. So these are the dual weights that I don't think I have the time to get into, but if you are familiar with graph theory, you would have seen these things in the context of matchings, min cost matchings. So, right, so what we will show is that our algorithm is essentially computing the optimal transport for this set. Okay, and the way we show that is the following. We're going to go to the cost scaling paradigm. In the cost scaling paradigm, one of the facts that is used quite commonly is that you can always replace the cost of an edge with the slack of an edge with respect to the dual weights, and it does not change the optimal solution. So you can replace your cost with the slack, and the key observation we make is in the slack space, if any edge has a slack greater than 4n plus 1 times delta, then it cannot carry any mass in the optimal solution for this scale. Okay. So this is so at a high level, this is the main idea. If I ask you what is the region which has slack 1, right? That will be precisely the region that has slack 0 once you increase the weight of this by delta. So when you do that, you get this region here that consists of all the cells of a delta that has slack 1. And if you increase it by 2 delta, then that will give you all the regions that have a slack of 2 delta, and so on. So that's the observation we use. And like we discussed, we take the arrangement. So when we take the arrangement, every cell in that arrangement, if you take any 2 regions of A delta in that cell, it will be indistinguishable to every other point of B. And so what we can do is we can basically condense them into a single point because they're indistinguishable. You can convert them into a single point, and that's what we do, and then solve the discrete OT problem. And like I said, the optimal solution with respect to the slack is also the optimal solution with respect to the original cost. And so what we get is the optimal solution with respect to the original cost, like we desired. All right, so an interesting feature of our algorithm is we not only get the epsilon closed transport plans, but we also get epsilon closed dual weights or weights on the points of B. So whatever the optimal weights are, we get very close to the epsilon close to that as well. Okay, so we have made further improvements, and I'm going to basically.
How can that be? There could be multiple optimal weights. Even in the network flow, there could be many, so the weight, there could be multiple
Weight assignment.
Yeah.
So it converges to epsilon close to one of the optimal solutions. Yes. I think it can be shown under reasonable assumptions. I mean, I understand that if this continuous distribution was a discrete distribution, then there will be multiple possible solutions. But if it's under reasonable assumptions on the continuous distribution, is always a unique solution, and that's something that can be shown. Okay. The improvement that we made is the following. If you see, our algorithm was sort of using OT solver as a black box, right? Instead of that, we actually come up with an algorithm that basically maintains, translates the ideas of augmenting paths, combinatorial ideas such as augmenting paths into the continuous setting. So what we do is we basically maintain some sort of partial transport plan that transports mass from B to regions that are within 2 shifts of the weighted Voronoi of B. And then we define idea of admissible triples. Basically, imagine this region here is B2 is transporting mass to this region, but this region is closer to B1. Any such triple that you have, we call it an admissible triple. And then we define the notion of admissible augmenting paths, which is basically a set of admissible triples. Like if you take any 3 contiguous triple, then that will be admissible. If that's the property, then you get, and then the starting and the end points have some free mass. Then we end up getting an admissible augmented path. And what we do is we basically, like in graph theory, we augment the transport plan along this path by simply flipping the edges. This means R1 will be assigned to B1 instead of B2, R2 will be assigned to B2 instead of B3, and so on. Right? And by doing so, we are able to augment the transport plan. And when we cannot find any more augmenting paths, we adjust the weights of B to find more admissible augmenting paths and continue the process. So we have guaranteed that by doing so, we actually can improve the execution time substantially. So if we use the earlier algorithm for 2 dimensions, the running time of that algorithm was a high degree polynomial. But we can improve that to n to the 4 by using this sort of approach. Yeah.
So what's 5?
This is the query. So when dealing with continuous distributions, I may have to query a triangle and ask what's the mass inside the triangle, right? I mean, all these regions that I get, and I choose a representative point, I want to know what's the mass of the continuous distribution inside the region. So we assume there's an oracle that can answer that in this much time. So phi is the query time of that oracle. Yes. So just to conclude, so this is this work sort of takes ideas from graph theory and extends it to continuous setting. So one question for us that we've been very interested in is, can we bridge the gap? So first of all, can we design exact algorithms? Right, that's a big open question. Even for simple settings, this will be an interesting question. Second, can we bridge the gap between the execution time of semi-discrete and discrete OT in 2 dimensions? And finally, in many applications, we are interested in computing partial optimal transport, not transport plans that transport all the mass, but alpha fraction of the mass. So there's no, can we come up with a clean representation of an optimal solution for a partial transport plan, and can we design algorithms to compute those? So these are the open questions that I would like to conclude with. Thank you.
So just one clarification. So the approximation in your algorithm comes because you are stopping when it's close to it's smaller than epsilon.
Right.
That's
right.
the only place, right?
Yes, that's right.
Okay, and there is no way of assuming that things are at least one or something.
What do you mean by that?
No, like sometimes if the minimum, let's say H weight is like 1.
Right. So that's a problem with the continuous distribution. In
Yeah,
graph
yeah.
theory, what people do is oftentimes they assume the edge costs are integers, and suppose your cost difference, the epsilon falls below 1, then you have the optimal solution and you stop at that. But here you're dealing with a continuous space, and so you cannot make that assumption, and that's part of why we end up getting epsilon close using scaling approaches. And that's where perhaps an approach like the Hungarian algorithm, if we can make it continuous, or make it work in the continuous space, maybe we'll get interesting exact algorithms, for this problem. But with scaling, I don't see how we can do that.
Sure. Yeah.
So is it clear that there might even be a rational solution? So it might be that the weights are irrational.
It's possible, and this is also true in math, like graphs, right? I mean, if you take like Euclidean point sets and you're dealing with irrational numbers, then
No, I mean, my point is I give you
Exponential time.
Yeah.
I mean, but you have to compute the exact solution,
Exactly.
exact optimal solution.
But that can't. I mean, I'm saying ostensibly that all the points are at rational. So the discrete distribution is completely rational.
Okay.
The continuous one is a parameterized one again with rational parameters.
Okay.
The optimal weights are irrational.
fair enough. Yeah, that's possible. Yes.
But then there is no exact computation. I mean, then you have to either do like existential computation or
Yeah.
Big computation is
yeah.
you have to round it.
I mean, there's always a rounding error if you're dealing with finite bit complexity.
That's right. Yes. Yes. I mean, there are ways around it.
You can change
But-
the computation model to.
That's right. Yeah. But I mean, we can. Yeah, I can think of many different ways to sort of handle this issue.
Can you please go back to the slide where you had this bound n to the power 40 log delta? Yeah.
Yeah.
So this n to the power 40 you just get because of this you are discretizing this entire volume and this
That's right. So we take 4n plus 1 shifts of the weighted Voronoi cell and then we overlay them and compute the arrangement. And so the number of cells in the arrangement is n to the of t.
So I was wondering that, okay, so this mu is the continuous distribution here, right?
Mm-hmm.
So, and right now I think you are assuming a very general mu, so no differential assumption at all. So I was wondering that if this, I'm coming from this function approximation in over spaces thing. So can you think of a way where this n to the power OD can be be improved like something if I tell that mu is beta times differentiable, then this can be made like n to the power OD by beta or something.
So if we are willing to make assumptions on mu, I think you can. There is hope that you can get this down to something like constant to the d times n, or but d in the exponent cannot go away, at least if you want polynomial time algorithms, because there's some hardness result that says you cannot get algorithms that are polynomial in both d and log 1.
So in the worst case, yes, I agree. But let's say, again, I'm not in this
I see.
domain. So what I'm trying to say is like, if you try to approximate a function, let's say in solver spaces, which is like d times differentiable, then you can just get rid of this n to the power d, and you can just, let's say like if you mu is like a uniform distribution, then
Right.
probably
So the hardness is for uniform distribution.
okay.
Yeah, and only a discrete distribution with 2 points, and it sort of reduces, rather, if they use the knapsack, computing volume of the knapsack polytope for the reduction.
Okay, so you are saying like this cannot be.
Yeah.
It's surprising. Uniform distribution.
Yeah.
Yeah. So what is the motivation for that 4n plus 1 shift? I mean, what's that 4n plus 1?
So why does it come? It comes from this fact that if you so if you think of what we did in the proof strategy, right? Sorry. Yeah, we discretized our space into the continuous region into exponentially many discrete points, right? But now you have this case where you have a bipartite graph where one side is n points, the other side is an exponential size graph, and you're solving an optimal transport between these two. What happens is, if you take the optimal solution, or cycle augmenting paths or alternating cycles in this, it's still going to be of size n. Right, because the smaller, they're simple cycles or simple paths. So the smaller of the two sets will sort of determine the length of the path in the bipartite graph. And what happens is we can sort of use some of the tricks that are used in cost scaling, which is if you take the optimal solution from the previous scale, the edges of those will have really small slack in them, right? And we sort of bound the slack by 4. So that's where, using that analysis, we're able to sort of show that no edge with a slack greater than 4n plus 1 delta will carry any flow in the optimal solution for the current scale. And essentially, we can ignore all these edges, right? And those edges which have slack less than 4n plus 1 times delta are actually captured precisely by these 4n plus 1 shifts.
In the interest of time, if there are further questions, let's take them over coffee.
Hello, can you hear me at the back?
Right, welcome back everyone. Next up, we have Professor Shujoy Kore, who is a faculty at IIT Bombay. Shujoy did his PhD from Ben Gurion University and followed it up with postdocs at TU Vienna and ULB Brussels. His research interests lie in discrete and computational geometry and combinatorial optimization. And today he is going to give us a talk titled Sketching and Uncertainty Through the Symmetric Lens. So over to you, Shujoy.
So thanks everyone for attending my talk, and first of all I would like to take this opportunity to thank the organizers for organizing such a wonderful event and also for inviting me to give the talk. And so the two themes that I want to talk about is sketching and uncertainty, and I believe that this is kind of the holy grail of modern day computation. I'll explain why. And of course, this is the topic I'm most interested in, that's why I'm trying to sell it, but I'll give some reasons. Of course, the commonality is geometry, so I'm looking at all of these problems from the geometric angle. So let's get started. Let me give a motivation to this, that why one should be interested in this kind of problems. So there is this wonderful workshop happening in Bangalore on geometry and algorithms. Believe me or not, this is my first time in IISc, first time in Bangalore event. So I wanted to know that how do I get there? And this is the air traffic route map of India, which is like anything, you cannot make anything out of this. This is like super dense, lot of routes, different color codings, and so on and so forth. So let's abstractify a little bit. These are the main important hubs, and you have a lot of international connections, domestic connections, and so on. And of course, you want to build systems which are in some sense light, which are less expensive, and systems which are sparse, that uses somewhat less number of connections. But then on the other hand, the other side of the story, data is hardly certain. It's no longer the classical computation regime where you have complete certainty of that input at the beginning of the algorithm and then we start the computation. We don't have this anymore, and the data is updated over a period of time. So these are the 6 important air hubs in the country. If I look at the fine-grained data of Mumbai airport, which I just downloaded like a few days back, so Mumbai airport alone handled roughly 53 million passengers in 1 year. This is a 20% hike from the last year, 3,500 flights per week, and 8% new routes they have added in last couple of months. This is a staggering number for me. How do we handle this situation? And to make this scenario worst, they actually have 2 runways which are intersecting each other due to the geographical constraints, of course. It's an island city, sea everywhere. So you want to build systems which are futuristic, which are sustainable, that don't fail often against like the adversarial inputs. So what is the solution to this? You want to build network systems like spanners, tree covers, TSP, and beyond, and all of these kind of optimization questions. In short, give me a sketch that we cannot refuse for a long period of time. Okay, so let me get into the theoretical sides of things. So let me define what is a spanner. So we have a metric space, a finite metric space with a set of points P, and a delta is the distance function. So a graph is a T-spanner for some real value T if the distance between every pair of points is preserved up to the factor T. So this is also called the stretch factor or the dilation factor. So let's look at an example in L2 norm. So let's say that we have these 4 points. This is the complete graph. If I report this as a spanner, then it preserves the dilation up to factor 1.5. So spanners were formally introduced by David Peleg and Schaffer around 1980s. And since then, if not the most, it became one of the most important graph structures, which has been very extensively studied for last 3 decades. Due to many different reasons, it has applications in different domains. For example, compact routing scheme, distributed queuing protocol, load balancing, efficient regressions, topology control, and many other things. And over the years, there are many different kinds of constructions that have been proposed. To name a few, different types of greedy spanners, bounded degree spanners, WSPD based spanners, and so on. Very recently, there is this new kinds of constructions, locality sensitive orderings, and many other types. So until 2007, everything is very nicely summarized in the book of Narasimha and Smith on geometric spanners. But then also a lot of things happened in the last 15 years or so. So let me define formally that what are the fundamental parameters of spanners. So of course, we want to build sparse systems, right? So how do we measure the sparseness of a spanner? It is the number of edges in the spanner to the number of edges in the MST. Why MST? Because a tree is the smallest possible connected structure in terms of the sparseness. So if I look at the same example, this is actually gives us sparsity 4 by 3 if you report this as a spanner. Right? So question is that how sparse a spanner should be. Well, you want the stretch factor to be arbitrarily close to the optimal stretch. You want the distance to be preserved like almost optimally, so 1 plus epsilon, of course. And preferably you want linear number of edges. Yeah. So Chu showed in Sausage 1986 that you could get a linear number of edges with stretch factor square root 10, and then later Clarkson gave 1 plus epsilon spanner. Delaunay graph is already a good spanner. There are also theta graphs for designing spanners in 2 dimensions, which were later generalized in higher dimension. So the first question I'm interested in is this trade-off between the stretch factor 1 plus epsilon and epsilon to the minus t plus 1 tight. All right. So let's move to the other side of the story. We want less costly solutions as well. So how do I define the cost of a spanner construction? It is the sum of the edge weights to the weight of the MST. We know that MST lexicographically chooses the edges. Therefore, MST is also like the least costly solution. So we can charge against this. The same example where we gave, where one can see that the lightness is same as sparsity if you report the outer cycle as your spanner. Light spanner has its own side of literature. We know that greedy spanner already gives constant lightness. In fact, it gives a lightness of epsilon to the minus order d. So already there is a 60-page analysis of epsilon to the minus 2d. We know that greedy spanner also gives a good spanner in metric space of bounded doubling dimension. So the question Rao and Smith asked in stock 98, what is the best possible constant in the exponent? Right? Greedy spanner is just you sort all the edges and then you choose like a in the reverse direction and see that if you already have a 1 plus epsilon path between this pair or not. You don't take the edge, yeah, otherwise you take it. That's all. So this is the general landscape for general graphs, the Euclidean setting, doubling and minor free. And I want to mention that sparsity and lightness is not just the complete story. People also look into hop diameter, degree, and many other different parameters, and they bring a lot of different level of complexity. So the first thing that I'm interested in this talk is Lee and Solomon in their Fox 2019 paper had a breakthrough observation is that if you use auxiliary data, I mean additional points which were not part of the input initially, this can actually substantially improve the bounds on lightness and sparsity. If you think about it, this is slightly counterintuitive. It's like we are adding more inputs and we are expecting that these values will go down. And this happens due to the magic of Euclidean space actually. It doesn't happen in other metrics.
No, but even for other metrics, you have these embeddings, right?
Yeah, through embeddings you can, yes. But then with embedding you already lost some distortion and that will affect your, yeah, so the dilation. Right.
So when you measure the lightness and sparsity, do you compare against the original set of points or with the standard?
Original set of points. Standard points don't count. Yeah, otherwise it's just the same. Yeah. Sorry? So what Lee and Solomon showed that in 2 dimension you get a lightness epsilon to the minus 1 over log epsilon to the minus 1 and also sparsity like epsilon to the minus half and so on. Then in a subsequent work in ESA 20 they showed that this is tight but up to this factor log delta. Delta is the aspect ratio which can be very bad at times, like it can go to log n. So this is not settled. Then later in stock 23, they gave an upper bound for the lightness epsilon to the minus t plus 1 by 2. So this was our starting point. I'll come back to the, yes?
How do these values compare to the values upper and lower bounds if you cannot use Steiner points?
Oh, so if you do not have Steiner points, then you have a quadratic blow up on the, I'll come back to that actually.
Okay.
Yeah. So actually previously I showed, right? So this is without Steiner points.
And this is an upper bound that you can
Right.
use. And this is a lower bound that says you cannot get better?
Yes, but I think, yeah, so there also you have a quadratic gap between the without Steiner and with Steiner.
Okay.
Actually, this is tight. This is the lower bound. So yeah. So I want to highlight that this phenomena of improving the value of the construction is not entirely new. Of course, in this context, this was new. So by Mikhail Elkin and Solomon, they observed that in the single source setting, so the single source setting is like this. Imagine that you have one point which is very far away from everything else, and I want this distortion guarantee between this point and every other point from that other cluster, right? So let's say that all of these points lies here and this point is somewhere here. So basically I want to build a construction where I can just charge against this distance, because this distance is very large. So hopefully we can build something that will preserve the distance factors and is chargeable to this. So there is an exponential improvement on the lightness in a metric space by Elkin and Solomon, and especially in the quadratic improvement in the Euclidean space. This was shown by Solomon. This is called the shallow light trees. So as you can see that, like to come back to Andy's question, in the single source setting, if you do not use any Steiner points, then the weight is 1 over epsilon. But if you use Steiner points, then it is epsilon to the minus half. Then for some regime of epsilon, this can have a big influence. So what we show is that we get a lower bound now, actually shaving this extra log factor, and their lower bound was only in 2 dimension. We get a lower bound in any arbitrary dimension for both lightness and sparsity. And for lightness, we show that in 2 dimension this is actually tight. So we can match our lower bound in 2 dimension. For 3 dimension onwards, Lee and Solomon almost matches this bound up to this factor plus 1. But this is a very important open question to match this completely. So let me give a very brief glimpse of our construction, that how do we get these results. So let's start from something very basic. In order to get a lower bound for this, we need to be able to find some mechanism to whom we can charge, right? We have this metric space, we have points, like how do we charge this? So the first observation is that between a pair of points, if you are expecting to have a 1 plus epsilon path, I don't know how this path look like, but I know that this path must stay inside this ellipsoid with foci A and B and the great axis 1 plus epsilon times AB. If it goes out of this, I will not be able to close this 1 plus epsilon guarantee. That's very good, because now we forget about the points actually, we can charge these ellipsoids, right? So if you have this kind of parallel ellipsoids, they come for free in the lower bound. But that's not all. So you also have this kind of slanted ellipsoids, because you have these parallel pairs, not just the parallel pairs but also other pairs. And there is a problem, because you can have a lot of ellipsoids that have a common space. And maybe in the lower bound we are charging again and again, and how do we fix this? So we take help of directions. We say that, well, we will look into one particular direction and see that which edge is existing in what direction. Because between a pair, if it doesn't fall under the right direction, we don't need to care about it in that particular spectrum. So essentially you show that, yeah, you are not really overcharging more than some constant number of times, and then everything works out. So the construction is as simple as what I showed. In 2 dimension, it is like the just this equidistant point snapped over two sides of the box. In 3 dimensions, you have this cuboid, you build this grid and you snap it on the other side. And this gives us the lightness and the sparsity bound. Let me move to the upper bound, and it's a nice geometric construction. So we show that in 2 dimension, for every set of points, you can claim the lightness 1 over epsilon, and this is tight. This uses actually 3 components. So one component is directional spanner. Second component is a generalized notion of shallow light trees. And the third component, so window partitioning scheme is a very commonly used computational geometry tool. We modify it a bit, so we call it modified window partitioning scheme. So let's start with directional spanner. So you have direction of a segment is just defined by taking the angle with a line parallel to the x-axis, and an angle bounded path is that if all the segments in that path follows this particular direction alpha. And a directional spanner is a geometric graph. So you take a particular direction and you build the spanner only for that. Now you combine all of these things together, you get a directional spanner. So it's a geometric graph together. Okay, so let's think for a moment, what do we have in our hand? Like, to whom we can charge? We can charge against MST. MST comes for free. It doesn't matter if it is L2, L1, so we will fall back on L1. So let's start with rectilinear MST. These are all different directions. So for every directions, I'm going to construct a rectilinear MST, and then I'll do something. What is that something? Is that, so the hope is, when I'm talking about this particular direction, let's say pi by 2 minus square root epsilon to pi by 2 plus square root epsilon. So with respect to every tile, I'll find a way to travel between this pair of points. But the question is that how do we travel? This is like an ambient space. It's completely vacant. You don't really have points there. But we have shallow light trees. And one way to think of shallow light tree is it's a net construction in the underlying space which will allow you to jump from one place to another place in a light way. How many shallow light trees? One is clearly not enough. This is not single shore setting. So I have to go from this point B to A. How do I go there? So you say, okay, let's pack 2. That's also not enough, because if I have to go via C, this is a lost game already. So what do? You say, okay, let's pack a lot of shallow light trees. So we take a particular direction and we keep packing shallow light trees. But it will have a huge blow up in the weight. But like always, geometric series comes to your rescue. So you can charge against the highest value over here. So even though you are like packing many shallow light trees, it wouldn't really matter. That's okay. But then let's come back to the previous question. I showed you the picture of a rectangular tiling, right? Who gives us rectangular tiling? We actually have a MST. MST is not a rectangulation of the space. MST will give a weakly simple rectilinear polygon. So it's very tempting at this point to say, let's just extend it all the way. Let's make it a rectangulation. But if you do that, you get extra log n factor to this. Okay? So we'll say, okay, we're not going to do that. We will do a histogram partitioning of this. We'll break it into more complex spaces than rectangles. But the moment we move away from rectangles, shallow light tree is gone. Shallow light tree is defined in the single shore setting in a very simplistic form. So let's revisit shallow light tree and have a more computer science understanding of this. So one can think of this whole space that it is a binary partition of this, because every time you kind of go down. So essentially what is happening is that you have a lot of points in the baseline, right? You have one point at the top. Much of the expansion of the tree is happening at the ground level. So they don't cost as much as it looks like. But now we don't have a flat space, we have this kind of stair type of situation, which means I have to charge these boundaries as well. see that now this binary decomposition will actually intersect this. But the observation is that this vertical portion of this charging doesn't matter, because this will not affect in the cost. And the horizontal portion of this charging, if you actually take the projection, it is same. It is exactly charging this baseline. So everything works out actually. So we can get a shallow light tree for this system in epsilon to the minus half plus L. So then let's come back to this idea. You have these super nice staircase polygons. Let's pack shallow light trees in different directions. And so we can handle rectangles, we can handle staircases, and then one would say that, okay, is that histogram good enough? It is not. So due to a result by Mark and Mark that from 94, it shows that you gain again a log factor. So all work, but we gain nothing. So at this point, I feel like we don't want to give up on this. And what is the fix? Let's make these things a little bit wiggly. So we have the concept of directions. We have this concept of angle boundedness. So why don't we just make these things like an angle bounded path? Now this becomes like a rabbit hole, and I don't want to get into this because there are many different kinds of constructions. So I'll just skip through this. So essentially combining everything, if you trust me, we get this bound 1 over epsilon. Okay, so the main important open question here is of course to close the gap of Lee and Solomon's stock papers epsilon to the minus d plus 1 by 2 and make it like a minus d by 2. And also one can ask that we are using a lot of shallow light trees, so which means it will incur a lot of Steiner points, and in a rough calculation it is like cubic number of Steiner points. And if you care about optimizing that, it essentially means you are asking the question of simultaneously give a bound of sparsity and lightness, which is a super interesting question, of course. We looked also beyond Euclidean regime. So question is what happens to planar domains, including polygonal domain, polyhedral terrain, or planar matrix. So polygon with holes, polyhedral terrain due to applications in robotics and many other fields. So one observation is that polyhedral terrain generalizes polygonal domain. And then you ask this rhetorical question, what is a perfect sketch after all? And I spent almost 20 minutes on describing how great spanners are. And now let me tell you, I don't believe that is the perfect sketch. The perfect sketch is actually tree cover. And let me argue for 10 seconds why do I believe that. No offense to spanner, by the way, I like them very much. So you see that trees allows you to implement them efficiently so that you can make queries. Spanners are not that good as a data structure. So tree cover essentially says that you get a collection of trees such that the distance is preserved in one of the trees. And this famous result by Arya et al. From 1995 already showed that Euclidean space has a very nice tree cover. We experienced some unexpected phenomena actually for polyhedral domains. So we get a superlinear lower bound of n log n for the stretch 2. So you cannot expect a linear scale spanner. But if you go a little bit beyond, if you take 2 plus epsilon, then linear number of edges is sufficient. This is a work in Soda 25. And so as we have observed that it is not possible to go beyond this factor 2, so you will compromise with that and by adding more points, let's say Steiner points. And in that case, we can construct 1 plus epsilon spanner with almost linear dependency. It also generalizes to bounded genus graphs and so on. And many results apply to deformable spanner, reliable spanner, low dimensional embedding, etc. I have very limited time, but I want to talk about uncertainty just to tell one particular phenomena that I have experienced while working on this type of problems. So typically when you think of uncertainty, there is a common understanding in geometry is that the cost function of an optimum solution in the online regime is typically monotone. It monotonically increases. If you want to make it non-monotone, you have to go to the dynamic regime, but then in the dynamic setting, you are not maintaining the solutions explicitly, so different regimes. I want to show that for certain problems, even in online regime, you experience everything together. So, so in the online setup, of course, you don't know about the point set. You don't even have information what metric you are dealing with. So their points are arriving like a one by one. Now, because of the online constraint, you can add something to the construction, but you cannot delete anything. Of course, you will measure it with the so-called competitive ratio, supremum over the sequence. Opt in hindsight knows everything, and algorithm is charged based on that. So the first question is that what are the best possible bounds one can get for online T-spanners? And now let me talk about this phenomena. So let's say that these are the 3 points that an adversary inserts one by one. Okay, so at this point, if I want to maintain a 3 by 2 spanner, there is really nothing to be done but to add this triangle. There is no other option. So adversary looks at this and inserts a point right at the middle. So the whole construction is compromised because this is this classic Steiner ratio, right? We should actually take this now as a spanner. Yeah, but we cannot do this because we have already committed to this construction. So this will come as an extra cost on top of this. But one will say, it's okay, this is the Steiner ratio. It's not like too much drop or up and down of the cost of the optimum solution. Let me show you another problem where it changes drastically. So I believe all of our favorite problem, matching, is very classical, and one would want to know that what happens to matching. So here is the setup. So I want to maintain a perfect matching, and every time 2 points are arriving in pair, and you want to maintain a mean cost perfect matching at all times. This is an adversarial sequence. I call it the curse of non-monotonicity because the optimum solution oscillates very rapidly. So let's say that we are dealing with step I, and these are the pairs that adversary inserted so far. This is obvious that what is the matching. You cannot do anything else because otherwise the cost of the matching will just increase. It's not competitive to any solution. So adversary looks at this scenario and inserts 2 points right at 2 end. So you have to, if you want to maintain an exact matching, you have to flip through the entire solution. So there is this concept called recourses, which is like how many changes you can make. If you don't want to make any change, you can't do anything for matching. But then one can say, can you maintain an approximate matching? And it is a valid question because in a breakthrough by Amit Kumar, Anupam Gupta, and Albert Gu, they showed that indeed this happens for Steiner tree or for spanning trees, for example. You can maintain a constant competitive solution with a single recourse for every k points, which you can think of as a fractional recourse. But so one would be tempted to think, can I emulate this in matching? So you can revert some decisions, let's say. But if you revert only one decision, this gives you nothing. So let me show you a quick example. So let's say that after 2 steps, your point pairs are 0, 1 and S is plus 1. It's again obvious that this is the matching. And so adversary inserts these 2 points now. So you have to flip back to, like you have to destroy one of the edge and you, let's say, commit to this one or either that one. Now adversary puts these 2 yellow points. You have to get to this blue matching. There is no way you can get it from that previous step, no matter what you have done with only one recourse. So one will ask that what is the best possible trade between recourse and the weight of minimum weight perfect matching? So the state of the art from a previous year soda, we showed that this is log-log, and it is the best possible you can do against adaptive adversary. Of course, for oblivious adversary, our technique is via online metric embedding, and so as Siddharth pointed out earlier. So, but then if you go via embedding, you lose this distortion because of the embedding, and one can ask like, can I get anything better without going via this? So, how much time I have? 2 minutes? 2 minutes. Yeah, perfect. So, in this remaining 2 minutes, I'll just give. Why you are unhappy? So I'll just give one quick algorithm for online spanners. So this is a high dimensional spanner under L2 norm. So we show that you can get a Steiner 1 plus epsilon spanner with epsilon to the minus 1 by t d by 2 times log n times opt. So this uses two components. Actually, if we don't use Steiner points, then you get like d plus 1, and with Steiner points it's much better. So essentially the phenomena is this. So the adversary will keep inserting points in two ends. So you have to keep adding edges basically. How do we avoid this? We say that, let's just skip over all of this. So this animation for which I spent time, so I want to show. So the adversary is going to put this point PQ, and this is the direct connection. So we say that we are not going to make this direct connection. We are going to make a grid around it and create a shallow net in the underlying surface. At this point, this is a overkill. Why should one do a lot of this extra work? This will benefit us when so this is the spanner path. The next time adversary puts this different pair P prime, Q prime, and now you don't have to travel all the way here. You can just simply use the same construction again and again. So once you build this, this is over. So that's the basic idea. So it's a bunch of work actually. So we looked at different regimes for general metric, Euclidean regime. Also norms play a different role, because for example in L1 norm you can get a better lower bound than in L2, so depending on the constructions, in doubling spaces, lines, etc. Future direction, I think the most important, interesting question here is that if one can get a lower bound, which will have a dimension dependence as you go up. Because this log n is unavoidable. This comes from a construction we have in one dimension. So the interesting question is, what is this function on D? So with this, I would like to conclude my talk. Thank you for.
Time for one quick question, maybe.
Has this been studied for other norms beyond L2?
Yeah. It has been looked into. Yeah. In fact, this classical paper by Imasio Waxman on the online question, right? Yeah, so this was general. This is for the general graphs. Right? And then, so I think Euclidean spectrum only people started looking because Noga alone had a construction where he improved significantly in the Euclidean norm, the bound. So that's.
This is like different than the embedding viewpoint.
No, they are connected together. I mean, you can always go via embedding, but then the catch is basically every time you go via embedding, you pay that extra distortion. Yes, but now there are a lot of work in recent years for different kinds of embeddings, and maybe like so it's still interesting.
In the interest of time, let's take further questions over lunch. Join me in thanking Sujoy and up next, we have Professor Kevin Buchin who is a faculty at TU Dortmund. Kevin did his PhD from Free University of Berlin and followed it up with postdocs at the University of Utrecht and TU Eindhoven. His research interests lie in spatial networks, motion planning, and generally in algorithms engineering. Today he is going to give us a talk titled Geometric Spanners, Bounded Tree Width and Oriented Constructions. So join me in welcoming Professor Kevin.
Which is the presenter for this one? Yeah. Fantastic. And you can hear me? Fantastic. Yeah, first of all, thanks to the organizers. It has been a wonderful workshop so far, and I'm happy to be here. You see an and in the title because I couldn't decide on which result to talk about, so you will have several parts in this talks which are somewhat related because they're all about spanners, but otherwise unrelated. So I've decided, so I didn't know that we would get such a great introduction to spanners already in the previous talk, so I decided to start with a general introduction. And then the second part will be about bounded tree-width spanners, and then about oriented spanners. Okay. So let's go through this introduction still, maybe a bit quicker. So we now know already what spanners are, so I don't have to search for it. It wouldn't have helped anyway. Geometric spanners, a bit more useful. And as we now also already all know, spanners are about dilation or stretch factor, about spanning ratio, whatever you want to call it. So you're essentially interested in the detour that you have to make by sticking to the network. So, and here the detour is quite big, and we're interested in spanners, so we want to have the maximum such detour to be small. Yeah, so this is just again more abstractly, so we have a set of points. We want to connect them in a way that we have short detours, so the minimum spanning tree connects them, but detours can be very long. Complete graph would connect them, but we don't want to build that many roads. So what we're interested in is sparse T-spanner, sparse saying we want to have a linear number of edges, and T-spanner saying that we have a small detour. So I have this here kind of picture introduction also once more. So what we want to have for any pair of points is a t-path, so we want to have a path that is at most t times longer than the Euclidean distance, and if this is true for any pair of points, so like in this graph, for any pair of points, the detour is smaller than a factor of 2, so this is a 2 spanner. And just some more pictures of spanners, so you can imagine how the detour could be roughly 10 here between two cities in the US, and then if you decrease t, you will need more edges. So this is a plain 1.5 spanner. And generally the problem that we're interested in is given a set of points in R to the G, and points, you want to have an efficient construction of a T-spanner with at most orphan edges, and typically you want to have other properties like, for instance, as we will see in a moment, tree width. But let me first show you some general constructions, because we will build on those later. So kind of the most commonly used constructions, the greedy spanner, we've seen in the previous talk already. So what you do is you take all pairs of points, sort them by their distance, and then from short to long. If there's already a t-path, you don't add an edge. If there's not a t-path, so let's say this is the graph constructed so far, I'm currently checking this edge, then I'm comparing the shortest path with the Euclidean distance, and if this is more than a factor t longer, then I would add this edge, otherwise I wouldn't. And this is a spanner with lots of nice properties. I think the only complaint you could have is that it takes fairly long to compute, but n squared time is also quite incredible for n squared log n for spanner with this definition. Second construction, theta graphs, or also Yao graphs, they're very similar. We've also seen this in the previous talk. Essentially, for every point, you subdivide the space around it in cones, and then, according to some definition, connect to the closest point. So if you connect to the Euclidean closest point, that would be the Yao graph. If this is some kind of projected distance, this is a theta graph. And if you do this for every point in your point set, then you get the theta graph. And the nice thing about this graph is, okay, obviously it has linear size. It's not difficult to show that it's a T-spanner. And if you use enough cones, you get a 1 plus epsilon spanner. Then let me also briefly say something about plane spanners. In particular, the Deloy triangulation is a constant O of 1 spanner, also already mentioned in the previous talk. Yeah, so this is kind of, but I think it adds nicely.
Sorry for the spoilers.
Yeah, no, that's okay. So, what I wanted to say here? Obviously, linear size because it's plane. It's maybe also intuitively clear why the Deloy triangulation should be a O of 1 spanner, because if you look at the direct connection, for instance, between these two vertices, these 2 points, then and you look at the Voronoi cells intersecting it, then somehow it should be possible to construct a path using those. And that is indeed true, and therefore you have an O of 1 spanner. And there's lots and lots of work on plane spanners, a lot of that work focusing on getting spanners with bounded degrees. So there's a plane spanner with degrees at most 4, for instance. And final construction that I want to show you for general spanners, well-separated pair decomposition. Okay, this is fairly difficult to explain in let's say less than a minute, but the general idea is you look at all pairs of points and you partition this set of all pairs of points into well-separated pairs. So this is, you have these 2 points and those 3, so this is 6 pairs of points which are now separated in this well-separated pair, whatever that exactly means. And if you take, so this is a well-separated pair for these 2 points and those 3. And if you cover your point set in that way, or partition the set of pairs in that way, that's your well-separated pair decomposition. And if you now consistently add edges, just one edge for every well-separated pair, then you get a nice spanner. And so the reason this spanner is interesting, among others, is so you again get 1 plus epsilon. So this should simply say T-spanner. And if you do your well-separatedness separated enough, you get 1 plus epsilon. And the interesting thing is that it is very fast to compute. So that's my general introduction to spanners. Now let me start talking about new things. And the first is geometric spanners of bounded tree widths. So this is joint work with Caroline Brees and Torben Scheele. This is just the photo is that from Tuesday in the park here. Yeah. So that's a tree. Okay, obviously.
Is that a theorem?
Huh? What?
Is that a theorem? It's a tree.
It's a tree. Yes. Might be. Maybe a lemma, I think. Okay, so why would we want to have spanners of bounded tree widths? So in the previous talk, we saw lots more applications of geometric spanners, or here I only have listed a few. If you have a graph in this context, you might want to do further computations on that graph. And you might want to, for instance, if you have like wireless, you do a spanner for kind of some wireless communication, then you might want to color it, because this would allow you conflict, avoid conflict in a communication. But coloring is a hard problem. But if you have bounded tree widths, then you get polynomial time algorithm for these kind of problems. So combining this, hopefully, you have a nice approximation of your distances and can do fast algorithms on your spanners. So, let me briefly just say once what bounded tree width means. So bounded tree width means, so a graph has, so here's a graph. So for a graph you can find a tree decomposition. Tree decomposition is you have this tree here. Every vertex corresponds, so the vertices are called bags. So there are bags of vertices, so this bag contains A, B, and C. And what you want to have is that every edge in the original graph is in one of those bags. So for instance, BC is in this bag, it's also in this bag. And being in this bag meaning the two endpoints are in that bag. And for every vertex in the original graph, so let's say E here, you want to have that the vertices in this tree that contain E are connected. So these three, they are connected. So that is a tree decomposition. And then the width of the tree decomposition is the number of vertices, the maximum number of vertices per bag minus 1. So this has width 2. And then the tree width of a graph is the minimum width over all tree decompositions. So this is now, you can conclude that this is a graph with tree width at most 2, and actually exactly 2. So that's tree widths. Very briefly, because we use those in the arguments, graph minor. So if we allow deleting edges and vertices and contracting edges, like here, from here to that one. So that is in a minor, H is a minor of G. And why this is relevant for us is because if you take minors, then the tree width does not increase, and also planar graphs. Planar graph, you can get from this also. Planar graphs have tree width over square root of n. So that is, yeah?
So for bounded tree width graphs, we know already it doesn't contain large cliques or white cliques and these kind of things.
Yeah.
So wouldn't it give us sparsity bound? And just the bounded tree width graph itself is sparse.
Yeah.
But you want a linear this.
Yeah, so we actually do not, so the question was about sparsity. So we actually do not look at sparsity at all anymore, but simply ask for bounded tree width. So sparsity, yeah, you get. Yeah. So now our aim now is essentially to get a trade-off between dilation and tree width. So that is the trade-off we're looking at from now on. And okay, so considering that trade-off, first the lower bound. So if we want to have tree width k, then we cannot, in general, expect a dilation better than n divided by k squared. So there is a graph, this graph here, it's generalization. And this is now in 2D for now, but more dimensions come on the next slides. So tree width k. So this is graph. If you want to have tree width k, you will have dilation n divided by k squared. And the idea is that you essentially have a k by k. So the underlying grid here is a k by k grid. So overall you get n points. And the k by k grid has tree widths k. So if we can argue that any spanner which has a smaller dilation than this would necessarily have this k by k grid as a minor, then we would know that it has to have tree widths k. Yeah, so that's the idea. So here, for instance, k is 5. If I simply take the complete grid like this, then I get small dilation. I get dilation square root of 2, but the tree width is 5, so 5 being the k of the grid. If I now can have want to have smaller tree width, say 4, then I will get some more gaps, like this one maybe. And if I would have such a gap, then the detour would immediately jump to n divided by k squared. And of course, we cannot rely on having this kind of gaps, but you can show that essentially for if this is 2 points of the original grid, so let's say for instance these two, then for any pair of points in between, there has to be a path with low dilation. And if you concatenate those paths suitably, so then you get a path from P to Q that if you suitably contract it to P or Q, you simply get the edge PQ, and in this way get the grid as a minor.
Just like again is contingent on the fact that we're not using Steiner points.
I was wondering in the previous talk whether Steiner points in any way could help.
Also,
Not sure.
in the definition of dilation, like you're only allowing, you're not allowing contraction. That is, I cannot give you a spanner where the distances actually shrink.
What do you mean by that?
So I can't like place Steiner points and connect them so that a pair of vertices that in the Euclidean distance, so let's say 5 apart,
Yeah.
they now become 3 apart. So
No, that would in the Euclidean setting not work. I mean, if I start with kind of Euclidean distances so in a graph setting, then you could this could happen.
So I mean, we had something on that in the planar metric regime, it does help. So just because like a planar graph contains a 3, there's a minus with respect to k cubic, my guess is that it might help.
So I think the problem, I think it doesn't help because the problem is for these points to have a short path, then the path essentially needs to stay in this region here. And so even if you have kind of Steiner points somehow, you'll be able to construct this path, and I think you will be then still able to contract it to the edge.
But even that middle spaces, right? Why? I mean, you could add Steiner points there to make sure.
Yeah, let's discuss that later. Good. Okay. So we have this lower bound in 2D. It also works in higher dimensions. In higher dimensions, a bit more tricky because there the into the D grid does not have 2 grids exactly into the D minus 1. So you have to put in a bit of work there. So here's an example. This, I mean, if this would be true, this would have 2 grids 4, but it has 2 grids 3. So this is a 3D composition. But you can show that n to the D grid has 3 grids order n to the D minus 1. And then you can do the same argument as on the previous slide and get a lower bound of n to the k to the D divided by D minus 1. And now let me show you an algorithm that matches this lower bound. So you start with the Euclidean minimum spanning tree. You compute a set of subtrees, each having this at most this size and this number of subtrees. Now we look at, so the orange vertices are the ones that are incident to the edges that are removed by kind of going to those subtrees. So what we now additionally do is in each of those subtrees, we go through the edges from longest to shortest, and if that edge connects to of those what we call representatives, we remove it. So this would be the longest one here, we remove it. So now for every of those orange representatives, we only have one tree connected to that, and the orange ones are no longer connected. Finally, we build the greedy spanner on the representatives, combine that with those trees, and this gives a spanner, and n to the k, yeah?
So how you are creating subtrees?
Hmm?
How you are creating the subtrees?
So in the first step here,
Yes.
I mean you simply recursively subdivide until you get the right size. Okay, so the dilation is low because if I have 2 points, I can essentially I follow the path between those points in the spanning tree, and then at some point I might hit a representative, but then I can use the spanner on the representatives to get to this representative and then go to that point. Only problem here is that the spanning trees, I mean, we removed extra edges. Yeah, so here, for instance, this edge might be missing, so I cannot go to this representative, but then I can reroute this path to another representative. And essentially the dilation is bounded by the size of those trees, and that exactly fits. Concerning the tree width is simply the tree width of the greedy spanner. because we have the greedy spanner and then additional trees attached to the vertices, so that gives me, that doesn't change the tree width. So then we just have to look at the tree width of the greedy spanner, and it was recently shown that the greedy spanner has small separators, and that immediately implies that the greedy spanner also has small tree widths. So this is the tree width of the greedy spanner. If I plug this in, so k to the d divided by d minus 1 to the, this is d minus 1 divided by d, gives me the k. And then by tweaking the constants, it's not O of k, but k. So this matches the lower bound. Yeah. Just a few more results on bounded tree width, and then I want to talk about oriented spanners for the last 10 minutes. So if you have a planar graph, so this is a nice result, I think. If you have a planar graph with n plus and then only few extra edges, this implies that the graph also has small tree widths. And this extra edges is k squared relative to the tree width of k. And the nice thing about this result is that as soon as you have a spanner construction which gives you a very sparse spanner, it also gives you small tree widths. So this is only for planar. I mean, in general, this is not true. I mean, adding edges might increase the tree widths more drastically, but in the planar setting and just above n, this is true. And with this result, we can also, for instance, reuse previous constructions for planar spanners. So what I here, for instance, if we want to have a plane or n divided by k squared spanner with maximum degree 4, we take this paper that uses that gives you graphs with plane spanners with few edges. This is the one that gives you a maximum degree 4. Combine those, plug that into this bound, and we get this result. And one final result on graphs with bounded tree width, actually very bounded because k is 1. So and this mostly here because it was mentioned in this paper. You also so if you have equally spaced points on the circle and you ask for the tree spanner with minimum dilation, then there was this lower bound of 2n divided by pi minus 1. And what we also showed is that this tree here nearly matches that lower bound.
So this kind of highlights that Steiner points help significantly. Like you can use this effort like the Frank Nicole route or the hierarchical tree embedding.
Mm-hmm.
So it's a tree embedding, so k is 1 and the dilation is like log n.
Mm-hmm.
So instead of like it beats this lower linear 2n by pi, it improves it to log n and gives you a tree, but has made like lot of
let's discuss that later. Yes. Because I still have one part that I want to talk about. The oriented spanners, where I at least want to tell you what an oriented spanner is, and then a few, just show you a few results. So here, this is an edge of a graph, and as you see, it's oriented in one direction. And that is what we're going to do in the last part here. Okay, so here again, we're going to connect cities, let's say. Normally, so far we always had undirected edges, or you could see them as bidirected edges. But now let's assume, because of resource restrictions, like for instance in the street network setting, we are forced to use one-way roads. And then, so we want to have what we would like to have is a sparse spanner, but now every edge, so between two cities, I'm only allowed to use one edge, and that has to go in one direction. So I am not allowed to have this back edge here. And then the question is, what can we achieve in this scenario? So already for 3 points, the regular dilation in this setting can be arbitrarily large. So we have a slightly different definition of dilation here, and that is the following. We look at, for 2 points, we look at the shortest closed walk in the spanner that contains those 2 points. And we divide that by the minimum parameter triangle in the point that includes those 2 points. So this, you can see this as kind of the minimum length cycle in the complete or bi-oriented or complete bi-oriented graph. Yes. So here's an example. So let's say this is my spanner. So first of all, if you look at the denominator for any pair of points here, the denominator is simply 1 plus 1 plus square root of 2, because for any pair of points, if you just look at the point set, ignore the spanner, there's such a triangle. Also for A and C, there's this triangle here, because this is not about the spanner, it's just about the point set. So that's a denominator. If you now look at the shortest closed walk, so for instance, for AB, there's this walk. For AD, there's the same one. For DB, there's also this one. So this is actually the length of that triangle also. So all of these points have oriented dilation 1. Same is true for everything except for AC. So now for AC, you will have to do the following. You will have to, essentially you will walk along, how do you do it? C, you can go to D, you can go to B, you can go to A, then you can go to D, but then you have to use the edge BD a second time and go back to 1. You look confused.
So for any 2 points, you have to decide on the direction.
Yes.
Why not allow both edges?
That was motivation.
That was the motivation.
Like one day.
Because you have to. That is. So okay. So for us, the original motivation. The original motivation that I didn't tell you is if you allow both edges and then start trying to prove interesting properties, you can always say, just take for every edge, just take both directions, and then you can just use all results you already have, and topic closed.
Well, 2 approximation, or
yeah, 2 approximation. Yeah, but the most.
2 edges cost more than 1, so.
Yeah. So there is kind of a regime where this is interesting. Yes, but for many results, many results are kind of asymptotic, and then it's kind of nothing to show. And so that was our original motivation. But of course, this is highly relevant for resource-restricted networks. If you, for instance, in a city, you want to there the graph is already given, the undirected graph, but you will have to, because roads are narrow, you have to decide on orientations. You cannot do
so
the 2-way
you don't allow
traffic.
Steiner points, because Steiner points would give you. So you don't allow Steiner.
You don't allow Steiner points. Yeah. Here, Steiner points definitely I would would completely change the problem. Okay, so that's the definition. Here's kind of a table of a subset of the results that we have. Okay, so we started off in 1D because everything was hard in 2D. There's still plenty of interesting problems in 1D, but we did now come to work on 2D problems. So in the plane setting, for points in convex position, the greedy triangulation, or orienting the greedy triangulation, gives us a constant dilation spanner. Otherwise, we do know very little about the plane setting. For the general setting, so if I don't enforce planarity, then we can get a 2 plus epsilon spanner, a sparse 2 plus epsilon spanner. And let me just run through this animation. So this is points in convex position. We construct the greedy triangulation, then oriented consistently, and this now gives a constant dilation spanner. The idea being, essentially, for an edge, I would look at the minimum parameter triangle. If it's in there, then if it's in there and consistently triangulated, I'm happy. No, it's obviously consistently triangulated. If it's in there, I'm happy. If it's not in there, then there has to be another edge blocking an edge of that triangle, and then I use that one instead. If I cannot use that one, there has to be another blocking edge, but all of these edges have to be can't be longer, they can't increase in length too much, and then by a packing argument this works out. So that was a very brief summary of this. We also, for general point sets, greedy triangulations do not help, or have at least a spanning ratio of n. Example I will not run through now. Also other triangulations do not help. Last thing I want to show, or next to last thing I want to show. So we can get a two-spanner if we allow a dense graph, to more specifically complete graph. So we can orient the complete graph in a way that we get a two-spanner essentially going through all triangles from small to large, small parameter to large parameter, trying to orient them consistently. And then this gives me a two-spanner because if at some point I would have wanted to use a triangle but I wasn't able to orient it, then there has to be two other triangles that already blocked the orientation, and then I can use those two triangles instead to get a walk. And let me just, as a final result, so we can use the same idea to get a sparse spanner. So the idea now is somehow to select only a linear number of triangles such that we get something nice for all pairs of points. And then with this linear number of triangles, if we then orient them just as in the previous algorithm, then that works out. Just the linear number of triangles are a bit complicated to find. Essentially, we use a well-separated pair decomposition, approximate nearest neighbor search, and somehow this allows us then to get for any pair of points a relatively short path. The 2 is essentially the 2 from the previous algorithm. The epsilon is the epsilon from the well-separated pair decomposition plus a little bit of epsilon from the approximating the min parameter triangles. And that is all that I wanted to show you. Thank you.
So you showed for triangulation it's not good, but I was just wondering for planar graphs, is it like similar story?
I mean, so let me go to the triangulation. You mean this here? I mean, any.
Planar graph can have these kind of faces. Planar graph can have these kind of faces, and then is it any better?
I mean, so this only. This doesn't even show anything general for triangulation. That just shows that the greedy triangulation doesn't work. So one of my open problems is get something interesting for plain graphs. Possibly a different triangulation, possibly not a triangulation. But I mean, if it's not a triangulation, I mean, you can always add extra edges. It's just that the greedy triangulation in this setting is not a good idea.
So, but then what happens to Delaunay?
What happens to Delaunay? Excellent question. This already fails here because, so already on 4 points, the dilation can be out very large.
I understand your motivation from the city. I want to remain with this motivation, but tell you that a certain fraction of the edges are bidirectional.
Yes.
Is it a sensible question?
So this is always the first question. No, it was the second question this time. And yes, definitely, it's an interesting question. I mean, of course, it's as hard as the original question. So we want to get to that question at some point. I think there also, but you can use this as a starting point for other interesting questions that are not on my open problem list so far. Definitely, yes, should do that.
Going back to the motivation, so you said when you reduce the T, right? So you showed the map of US. So you said you need more edges.
Yeah.
But I mean, so if you're looking at it from a realistic context, so there should be some D up to which you can go, beyond which it won't be possible. I mean, you can't reduce D below a certain point, right?
Yeah. So this is okay. So let me go there. I mean, D. So you mean with D, you mean the dilation, yeah?
Sorry.
T, yeah, T.
In the T-spanner.
Yeah.
So you cannot reduce T below a certain point.
I mean, if you do not enforce planarity, then of course you can, the more edges you add, then you can do 1 plus epsilon. For planes, okay, I can go back. For plane spanners, so for the Delaunay triangulation, there is a lower bound. I do not know what the general lower bound for plane spanners is. I would assume it also exists. Maybe someone knows. Yeah, so there's certainly kind of a value which you cannot go below. Yeah.
If there are no more questions, join me in thanking Professor Kevin again. Thank you.